So I can actually do this either way. I'll let you all vote. I could either work through the homework problem first and then go over this formal material that I have to finish up, or I could go through the formal material first and end with the calculation. Which one would you prefer? Calculation first? Formal material first? Formal material first wins. Barely. Okay, I'm going to lose this because I hate it. Anyway, all right, so I just got three pages of stuff. We can get through this very quickly. At any rate, so I didn't really know where to put this in our development of the material, so I'm just going to kind of throw it out there as a last-minute observation. But you remember that in special relativity, we're working with the metric, which we'll conveniently label by eta, which is -1, 1, 1, 1, and zeros everywhere else. And this actually, you know the role that it plays. It turns vectors into dual vectors. And then the inverse of this, which happens to have the exact same form, takes dual vectors into vectors, okay? But I kind of want to show you some of its interesting properties, especially compared to the metric that we encountered in 3 dimensions. Because in 3 dimensions, the metric that we encountered was basically the identity, which is so simple that it's almost like it never gets written. Because who has to write the identity? It's just automatically understood everywhere. So at any rate, so what I can tell you is the following. In 3D, and by 3D I mean with this metric, if we want to write down ds squared, which is of course just the contraction or the product between a vector, a coordinate displacement vector and a coordinate displacement dual vector. Of course, since the metric is the identity, these have the same components, so nothing interesting is happening there. Then this just becomes dx squared plus dy squared plus dz squared, okay? And one observation which you can immediately make from this is that this magnitude of the coordinate differential is always greater than or 0. The square of the coordinate differential is always greater than or equal to 0 because it's the sum of a bunch of squares, okay? And moreover, it's only equal to 0 when the coordinate differential vector itself is nothing but zeros. I mean, I could write 0, 0, 0, but you understand what I mean when I write 0 here, right? This is a vector, it's got 3 components, all 3 components are 0, that's what I mean. Yeah, I mean, I could do it like this if that would make you physics 100 people happy. Anyway, now I want you to consider the special relativistic version of this, which we can obviously very quickly write down. First of all, we're going to index things with mu's instead of i's. In this class, whenever I'm talking about purely spatial directions, I'll go back to using the indices I, j, k. When we're doing all 4 space-time indices for or values for our indices, we'll use mu, nu, lambda. Okay, we won't do this very often in this class, but we'll mainly be in 3 + 1 dimensions. But at any rate, you all know what expression this is. It's minus c squared dt squared plus dx squared plus dy squared plus dz squared. Okay, this is of course built off of this, which has got the components c dt, dx, dy, dz. So the c comes into the story in the components of this vector. The metric itself is just ones. Okay? Now, let me see. Hannah.
Hi.
Hey, how you doing?
All right, how are you?
I'm good. All right, Cameron. I'm just kidding. Do you think that this obeys a similar property to this?
Sure.
Why?
Oh, wait, no. Well, there's a negative out front.
Yeah, there's a negative out front. So it turns out that depending on how big dt is, compared to dx squared plus dy squared plus dz squared, depending on the size of the relative sizes of those, this could be, or can be, plus, minus, or 0. Okay? So we definitely give up this obvious condition in this case that everything's positive. In this case, it could be positive if these win, negative if this wins, or 0 if they exactly balance. But, more interestingly, it can be 0 even when dx mu does not equal 0. Obviously, if all of the dx terms are 0, then this is equal to 0, right? I mean, it's 0 plus 0 plus 0 plus 0. That's equal to? Good, I was going to have to draw Cameron's card and ask him that. I don't have to now. But if you observe, as long as this is exactly balanced by this, it can be 0 even though this is a non-zero vector. That's quite interesting, right? Quite counter to the intuition you get in this case, all right? Now, another important thing is that ds squared is invariant. Okay? It's invariant, of course, because it's a combination of a vector and a dual vector. These transform in ways that are exactly the inverse of each other, so the transformation matrices cancel to give the identity. So, whatever sign this obtains when I crank it out, that is going to be the same sign that's observed in any reference frame, because changing your reference frame is not going to change the value of ds squared. So if something has got a ds squared which is negative, every single observer is going to see it as negative. If it's 0, every single observer will see it as 0, okay? Now, hang on. What do you think controls what the sign of this is? Say it again? Well, the dt term is certainly going to play a role, but the total sign is going to be somehow how this is combined with this. Because if this wins, it's positive. You know, so it's somehow got to take into account all of these. But I mean, you know, let's just pretend this is a one-dimensional or a one-spatial dimensional thing. So let's just ignore dy squared and dz squared for a moment. So you got minus c squared dt squared plus dx squared. What physically relevant thing do you think is going to determine the sign of this?
Velocity.
Exactly. Look at this. Watch. If dz equals dy equals 0, then what we can say is the following. If dx over dt is less than c, okay, I can get rid of the square roots because everything here is squared. I might as well just take square root of each thing. If that's less than c, then what is the sign of d squared? Cameron. It is exactly negative. Okay, let's just check it out. dx is less than c dt. So this, of course, means that dx squared is less than c squared dt squared. So if I just move this to the other side, it's negative. Okay? So that means that ds squared is negative. What about if dx dt equals c? Henry, Trulson.
You get 0.
It's 0, right? And last but not least, what if dx dt is greater than c? The other Henry.
He's dropping.
Yeah, I thought so. Joey.
Physics is broken.
Physics is broken? Well, no, but what is it?
Yes, for this.
Yeah, ds squared is greater than 0. shit can do this. We know certain shit can do this, and we know nothing can do this. So even though these are sort of dictated by how fast things are, we can also imagine this as being the separation of two events in space-time. And you can obviously have events which are separated by the need for a signal to go between them of this, which of course means that nothing can go between them because nothing travels faster than the speed of light. So what I'm saying here is we're going to use this language to notate a sequence of events that are designated as being time-like, light-like, or what is often called null, and then space-like. Okay? So let me actually draw a picture to sort of explain what this means. Oh, whoops. This is my x-axis. Okay? So if I just want to consider two events which are separated in a time-like fashion, well, first of all, dx dt has to be less than c. Well, let's take the simplest value of dx over dt. Let's take 0, because that's obviously less than c. If dx dt is 0, basically I can say dx is 0, because time is always going to tick. It doesn't matter. But your position can be the same. All right? So we can take two events which are separated by 0 in the x-axis. So we can take an event here and an event here that have the same x components, so dx is 0. So these are time-like separated. Okay? Conversely, we can take two events. Well, actually, let's go down here. We just need ds squared to be greater than 0. I can take dx to be anything and take dt to be super, super tiny. Okay, I can take this to be infinity if I want. I can take dt to 0. So I could actually label events here. And these are space-like separated events. Okay? And then last but not least, there is this situation where dx dt is equal to c. We're eventually going to set c equal to 1. So really this is just a line of slope 1 along which we can put two events. Okay? Now, I actually don't know if I teach you this in this course, which is kind of scary, but I'll just point it out. So events can happen in space-time that are like this, or like this. They're all perfectly allowed. But the question is, what about causality? Can this event be the cause of this event? Yes, because to be the cause of something, you have to be able to send a signal to the later event. Now these are events. Points in space-time are events. They have a position and a time at which they're occurring. Okay? So these aren't places, these are events. This thing can obviously send a signal here that travels less than the speed of light. It cannot be moving at all, and we'll get up there. Okay? What about this event causing this event? Can it? It can, as long as it's sending the signal to create this event by the speed of light. What about this event and this event? No. Okay? So if these two events were happening, say Jupiter and Mercury exploded at the same instant of time, they could not cause each other because light can't get from one to the other instantly. So it turns out that this is the sort of basis of a new adoption in special relativity of what we call causality. In the past, in Newtonian mechanics, causality was always based on the principle that the cause just had to be earlier in time than the effect, with no mention of distance, none. Because in Newtonian physics, things can in principle travel at infinite velocity. especially signals or whatever. But in relativity, nothing can travel faster than the speed of light. So it turns out that a really nice mechanism of determining cause and effect is to take an event and draw the light cone from it. Anything inside of the light cone for an event, that event can cause, including anything on the edges. Here, continuing it into the past gives you everywhere that could cause this event. And then everything outside of it is not causally connected to that event. Nothing out here could cause or be caused by this event. This is the past light cone, what could cause the event. This is the future light cone, what the event could cause. Does that make sense? We won't use that a lot in this class, but in general relativity, it's hugely important. Okay, so are there any questions about this before I move on to it's going to be a related issue. Okay, so remember, we talked about this last time, that the 4 momentum, okay, satisfies that minus e squared over c squared plus p squared, where this is the relativistic energy, this is the relativistic spatial momentum, okay? This always has to be equal to minus m squared c squared. And I took this and I extracted this very useful form of e squared minus p squared c squared equals m squared c to the 4th, and I said we would use that, and we will use that in the example that I'm going to work out later. But I, for now, just want to focus on this, okay? Here is the important thing. The designation of time-like, light-like, and space-like, it applies to this position displacement vector, but this categorization actually applies to any vector. We can take any vector and square it, okay? Here we squared it and formed ds squared. Here we square this and we get p squared. And if the square is negative, it's a time-like vector. If it's 0, it's a light-like vector. And if it's positive, it's a space-like vector, okay? In particular, this is the vector describing the momentum, okay? So if this ends up being negative, it's time-like. If it's 0, it's null. And if it's greater than 0, it's space-like. Okay, exactly the same way it played out up there, okay? Now, oh, Connor, you're gonna get to walk through this one with me, you ready? Okay. If this is negative, what is the sign of m squared? So if the left-hand side of this expression is negative, what's the sign of m squared? It's positive, because this is a positive number.
Yeah.
If this is a positive number, the right-hand side is negative. Okay? This is positive. You're walking through this with me.
This is really,
What if the left-hand side is 0?
0.
Then m squared is 0.
Oh, wait.
What if it's positive?
That would be negative.
It would be negative. Okay? There you go. This is the result with which you're all familiar. This is something traveling subluminally, sitting at rest if you care, just not going this at the speed of light. It has positive mass. To go at exactly the speed of light, that is to have a null trajectory, you have to have your mass squared be 0. And anything which is traveling faster actually has an imaginary mass. M squared is less than 0. But this is what we are often referring to as tachyonic. This doesn't exist, right? Right?
At least as far as anybody knows.
No, it does exist, and we're going to look at it later in the course. It plays an incredibly important role in the Higgs mechanism. but we'll give it an interpretation which will be far less interesting than the tachyonic one. Okay, any questions? All right, so let me clear the board and turn my attention to another form of the derivative which is important. Of course, last time we developed the for velocity and then defined the for momentum by giving a new parameter to parameterize trajectories through space-time, and that was what we call tau, which is the length of the path through space-time, and you can also identify it as the rest time. But there is another category of derivatives which you are all very comfortable with. You've seen them before, but I'm just going to do the four-dimensional version of them. So remember, in non-relativistic physics, del played a pretty important role. It can operate on fields. So for example, we might talk about del of a scalar field, or we might talk about del dot, the electric field. This is, of course, the gradient. And this is the divergence. Okay? And we do a time derivative. Which operates on fields. Okay, so we might consider the derivative of the magnetic field with respect to time, and particles. So for example, we might consider the derivative of the position to define the velocity of a particle. Okay? So how many of you have heard of this? How many of you have heard of this? Okay. Well, remember, when we want to do special relativity, which lives in 4 dimensions, we have to take things which were vectors in 3 dimensions and turn them into 4-dimensional vectors. This thing, it's a scalar in 3 dimensions, but in 4 dimensions, it's the component of something, because time is just the component of a 4-dimensional vector. So the question is, what would be the 4-dimensional analog of this vector derivative? What do you think? Drew?
You could just write del u.
Right, but what would the components of it be?
I guess it could be d by tau, because you don't want to use time.
Say it again?
D tau there, and then dx, dy, dz. Or
Do d tau?
dx0, I guess. dx1, dx2, dx3.
So the first term is d
dx0, I guess.
ddx0, so we want this to be that?
Yeah, and then ddx.
Yeah, and then ddx, ddy, ddz. Okay? So this is the 4 derivative, but this only acts on fields. You can't take this and apply it to a particle, because I mean a particle, what the hell is d by dx, d by dy for a particle, a point-like object? That doesn't make any sense. So this is a derivative which will apply to fields, like magnetic electric fields. Okay? Hang on. I gave this a lower index. Would you call this a vector? Or
A vector operator.
it is an operator, but is it a vector operator?
It's a dual vector operator.
It's a dual vector operator because the index is lower. But if you think about it, remember this vector was made out of c dt dx dy dz. Well, the c dt dx dy dz are all in the bottoms here. So the fact that this acts like a dual vector kind of makes sense, all right? In fact, it is exactly a dual vector, and the transformation of this follows the dual vector transformation rule. So it's going to be mu prime mu. Okay, which is the opposite of a vector transformation, or the inverse of a vector transformation. Now with this derivative in hand, we can take the 4 gradient, or the 4-dimensional derivative of a scalar, and this results in a dual vector. Because I'm combining a dual vector with a scalar, the result is a dual vector. But I can also take the derivative of a vector field, and what do I get when I do this? A scalar, right, because these indices are contracted, they're sum numbers, so this gives me a scalar. Okay? So it is very similar to what we do here. This del phi is a lot like this. It gives you the gradient, except, and here this gave us a vector. Here it's giving us a dual vector, but whether this was actually a vector or dual vector is kind of in the air. It's actually a dual vector. But anyway, this gives us a scalar, which is basically the same as this. Okay? All right. Any questions about that?
What about a curl?
No, we're not going to do a curl. We're not going to do a curl because a curl incorporates a cross product, and a cross product is really kind of weirdly defined in 4 dimensions. Because remember the way you think of a cross product? You think a cross product of 2 vectors in a plane gives you something orthonormal to the plane or orthogonal to the plane, right? That's what a curl does. Okay, well let me give you 2 vectors in 4 dimensions and you do the curl of them. In what direction does the result point? Orthogonal to the plane? In which direction? There are 2 directions orthogonal to every plane in 4 dimensions. There is an operation which is akin to it, it's just not as, it doesn't have that geometric simplicity that we give to story in 3 dimensions. Okay? All right, so are there any other questions about this? Yeah?
So you say partial mu is a dual vector, but it can't be in the same space as like, it seems weird to interpret that as a dual vector when just like a space-time event is also, are they in the same space? Is it the same kind of a dual vector as a spatial dual vector?
Yeah. So what do you, keep going on your question because I don't think I quite understand it.
So I think of a vector or a dual vector as like a point in the space in dual space. And I think of that
No,
space.
no, they're not points. They're not points in the space. They're actually, to be quite technical, and we would learn about this in general relativity, but not in this class or my grad math phys class, vectors don't exist in the space. They exist in the tangent or the cotangent bundles to the space. But that's a separate story. Vectors don't exist in space. You were born and raised thinking that they did because you learned about the position vector, right? This thing, that's a bunch of bullshit, because this has got to be with reference to some origin of the coordinate system which doesn't exist. There's no coordinate system to which we can, no, rather you say, okay, I'm going to take another point and then construct the displacement vector between the 2 of them. This vector does not live in this space either. This vector actually lives in what we call the tangent space. But that's something which we'd have to talk about outside of class hours. It plays a very critical role in general relativity, but in this course we don't really have to work with it. Or you could just take GR and learn about it there. Okay, now are there any other questions? Okay, so now we're going to answer this question in yet another context, and the question is, we've got the 3-dimensional version, let's do the 4-dimensional version. And so this is actually going to be a review, right? Because how many of you took ENM from Pat Cole? Yeah, so you've already seen this. This will just be a review. Anyway, yeah. So an interesting question is, the electric field has EX, EY, and EZ components. The magnetic field has x, y, and z components. What the hell are those going to look like in 4 dimensions? Ross, put your hand down. Okay, I mean, previously what we were doing was we were taking the spatial parts and just adding in a time component. That's what we did with position. That's what we did with velocity, momentum, okay? So we have spatial components. We have 3 spatial components for each of these. We want to promote them to 4 vectors. What can I put in the time slots? Sam?
That'd be like flux.
That's a good guess. It's a really good guess. Any takers? I mean, I can draw a card, but Jack?
I have no idea on that one.
That's fine. Go ahead,
Is it
Jack.
like a charged momentum or something?
No. So there's actually 2 routes to doing this. One you might have seen, one you probably haven't seen. First of all, it might just be, well first of all, let me say this. In non-relativistic physics, E and B are separate things. But if you actually think about it, E and B are kind of the same, or they're linked together. So it would actually make sense if I combine E and B together, because we know in relativity you can transform E into B and vice versa. So the first way to do it is to combine E and B into an asymmetric, which means if you transpose it, it comes back negative, which means that all the diagonal elements are 0.
Wouldn't that be anti-symmetric?
Anti-symmetric, sorry, yeah. Yeah, I have it written as anti-symmetric. Tensor, which takes the name F mu nu. So 0's down the diagonal, and then minus EX minus EY minus EZ, whoops, EX, EY, EZ, and then BZ minus BY, EX minus BZ, BY minus EX. Look at that, it's 4 by 4. This is obviously something which is well defined in 4-dimensional space-time. Okay? It's anti-symmetric. If I flipped it over the diagonal, I'd get back minus what I started with. All right. Oh, wait. How would this transform if I did a transformation? Oh, PJ.
Yeah.
How would this thing transform?
You need to throw 2 rotation or 2 transformation matrices.
Yeah,
Tensor code.
exactly. So remember, I'll just remind you, this is how I always pick the indices on the lambdas. I just start with this, and then I say, okay, I've got to get rid of the mu and give me a mu prime. So I got to have a lower mu prime and an upper mu. And then I got to get rid of the nu and give me a nu prime lower. Boom. That's how you do it. Okay? Now, before I move on, I want to ask you a very interesting question. Because you were asking me about a curl. Okay? Look at the F mu nu behind me. What do you think it would look like in 5 dimensions? It's pretty straightforward, right? I mean, you would do EX, EY, EZ, and EW, where W is the 5th dimension. Right? It's easy, right? What about B? How many B terms do you have to add? You have to add 4 of them, not 1. I mean, look at it, folks. If I expanded this to a 5-dimensional case, this is easy. That's easy. What 3 terms for B do I need? It's not BW. Not at all. I know. Kind of crazy, isn't it? You know what I could do to label this to make the answer obvious? Instead of calling this BZ, I could call it BXY. Instead of calling this Y, I could call it XZ. And instead of calling this X, I could call it ZY. Now you can guess what goes here. This is just harmonious with that idea that the curl, the cross product, it does not give you something which is along an orthogonal vector. It gives you something in the plane, which you should label by the 2 coordinates of the plane. Okay? But anyway, that's just my bitching about cross products. I'll just leave it in 4 dimensions and we'll just move on from there. Anyway, there is one more way to do this, which hopefully you've at least seen hints of, and that is we can also express E and B in terms of a scalar field, a potential, plus 1 over c dA times plus the derivative of the vector potential. And then the magnetic field is, of course, just the curl of that vector potential. So how many of you have seen scalar and vector potentials in your formulation of E and M? Okay? All right, so E and B, they don't get promoted to vectors. They instead get combined into that. However, this has got a spatial vector and a scalar component. These can be joined nicely into what we call the vector potential, whose time-like part is minus the scalar potential and whose space-like parts are just the vector potential A. Okay? Now, of course, the dual vector form of this would be phi A. Just change the sign on the time-like term, right? And we, of course, know that as a vector, this will transform appropriately. Whoops. Okay? All right? But now, we can recover all of this in a single, really simple expression. That is, this thing right here, the electromagnetic field strength tensor, can be obtained from this 4-vector potential by just doing this derivative, where this is mu nu and this is nu mu, so this is automatically going to make it antisymmetric. If I interchange mu and nu on this, I'll interchange mu and nu, which will just give me an overall minus sign. Okay? So just as a quick example, if I want to calculate the F01 term of this, that would be D0A1 minus D1A0, okay? And if you think carefully about this expression right here, then this is just going to be 1 over c dAx dt minus d phi dx. Okay. D0 is 1 over c dt. A1 is the x component of A, so that's this term. And then A0 is, of course, phi, and D1 is d by dx. If you compare it to this, that's just minus EX. Oh, look, the 0, 1 component of this is minus EX. Everybody on board? Okay, I'm going to give you a homework exercise cranking out another term of this, just to make sure. All right. Any questions? Good. All right, so now I'm going to do the example problem for you. And how many of you actually looked at that last question on the homework? Even though I know I sent an email saying you don't have to do it. Would you rather me do A or B? Or does it matter? Who says A? Who says B? All right, I need people to vote. Who says A? Who says B? Oh my God. I'm going to say A1. Just for simplicity. But at any rate, I think A is a slightly longer problem, but I'll get it banged up for you. So I just want to do this for you. It's in no way, shape, or form like something you should memorize how to do. I just want to illustrate to you some of the tips and tricks that can be used in solving problems like this. Okay? This isn't directly, even though we're going to eventually get ourselves into scattering calculations and decay rates, we're really not going to be focused on these kinematic problems, which is what this is. Rather, we're going to focus on the dynamics. We're going to actually be interested in calculating the matrix elements associated with it, but more on that later. All right, so this is problem 4A. And so we have the process AB, and they're going to go into C plus E plus F plus D, where A starts with energy EA, and B starts at rest. And this is all in the lab frame. Okay, so we're going to start by putting B down at rest, and then we're going to slam A into it. Kind of makes sense? And then, of course, all of this shit's going to come out, in different directions with various velocities and so forth and so on. And the question, just in case you don't remember it, is in terms of the masses of all of these, what is the minimum amount of energy that A has to have in order for this to be a possible outcome? Okay, so we don't have to worry about all the other outcomes, just asking whether this is even possible. Okay? So, all right. Well, first of all, let's ask this question, because this is going to help our calculation. And B is at rest, and A is coming in with some energy. First of all, if all of the masses are given, the masses of all the particles are given, how much energy does particle B have? Or what range of energies can particle B have? It's at rest.
It's rest mass energy?
Its rest mass, that's the only value it can have, because it's at rest. Particle A can have different values of energy depending on how much we give it, okay? Now, A's coming in with some amount of energy, B's sitting there with a fixed amount of energy. They're going to slam together, and then coming out of it are going to be all of these other particles, okay? Now, if I slam particle A into particle B really, really, really hard, and it makes all of these other particles, those particles may have energies which include their rest mass energy plus their kinetic energy, the energy of their motion, right? Well, energy is conserved, it's constant, so the energy of this coming in plus the energy of what's sitting there had better equal the final energy of everything coming out. So the question is, what is the smallest possible energy that you need to create all of those particles? What configuration corresponds to the smallest amount of energy that would be needed? They would all be created at what? At rest, exactly. Because if they're moving, they have more energy than their rest energy. So what we can say is at the end of this, if all of the particles are created at rest, then I've given A the smallest amount of energy that you can possibly give it and create these. If you gave it any less, it could not create these. If you gave A more, it could create them. They would just carry away that extra energy in kinetic form. Does that make sense? Because I'm about to use that extensively. Does that make sense? Yes. Well, you pick. Who goes first? You both got your hands up.
Doesn't the final momentum have to also be the same? So if they're moving.
We're going to go there. We're going to go there. We're going to go
Same
there.
question.
Huh?
Same question.
Yeah, same question. Okay, so one thing you have to remember is I'm actually going to ask you this in different frames. So what I'm going to do is I am going to look at A plus B in the lab frame, and then I'm going to look at C plus E plus F plus D in the center of momentum frame. Because in the center of momentum frame, these are all at rest. In the lab frame, they would all be moving together, but in the center of momentum frame, which is the simplest, we can say they would all be at rest. Now, how do I connect the lab frame to the center of momentum frame? You'll see how I do that in just a moment. Okay? But the setup of the problem is information given in the lab frame. The observation that they all must just be created with their rest mass energy is an observation that's most easily made in the center of momentum frame. Now let's work this out, and you'll see why I'm doing this. So first of all, let me do the total for momentum initial in the lab frame. So this is going to be the for momentum in the lab frame of PA plus the for momentum of PB. Okay? What does the for momentum of A look like in the lab frame? So it's moving in the lab frame. What does it look like? What does the for momentum look like? Yeah, this is generic. I mean, what's the first component of a for momentum vector? Don't make me draw a card. Energy divided by C. Yeah, so this would be EA over C, and then what is the spatial components? So the spatial components are just, yeah, they're the three spatial components of the relativistic momentum, so we would call this PA. Oh man, more noises. Okay? What about the 4-vector momentum of particle B in the lab frame? Yeah, so it's just going to be MB times C times 0 vector. The rest mass energy is mc squared, but you divide the energy by c, so you're left with mc. Which makes sense because this has the units of a momentum. That's just one thing you can check. I mean, these are momenta. They should have units of mass times speed, okay? So we can add this up, EA over C, PA plus MBC, okay? Then what we can do is we can say, okay, what about the total momentum final in the COM frame? Okay? Where what I want to do is I want to use the final momenta of this, which corresponds to the smallest value of EA. That is, all of these are at rest. So what is the for momentum of particle C in this frame? Say it again. Yeah, it's MCC, 0 vector, plus MDC, 0 vector, plus MEC, 0 vector, plus C, D, wow, CEFD, wow, man, that's crazy. I don't know why I did that. C, D, E, F, okay, yeah, it doesn't matter. Okay, well this is a simple one, MA or MCC plus MBC plus MEC plus MFC. Okay? Now, you ready? Let's use the conservation of momentum. P mu total I lab equals P mu total final COM. Right? That's just using the conservation, which is actually just the constancy of the momentum, because we've taken all of our colliding objects in our system, so there's no external impulses. So, right? Yeah?
Can we just compare different reference frames like that?
Say it again?
Can we just directly compare different reference frames like that then?
Yeah, I mean, these are two different reference frames. Does the vector in one reference frame equal the vector in another reference frame? Hell no. I mean, in the center of momentum frame, nothing is moving. But in the lab frame, things are moving. And there's no way these two things are equal. No way. No. Boom. Okay? That's shit. But it is the seed for something we can use. I really, really, really like the equal sign. How can we get this equal sign just by adding something to this? What do you think?
I mean, like the dual of each.
Exactly. What if I combine this with its dual vector and this with its dual vector? Because now this combination is an invariant. I can evaluate it in one frame, or I can evaluate it in another frame, and I have to get the same result. Does that make sense? So this is a trick that is often used in these calculations. You consider the invariant structures, and then you can connect one frame to another freely, because it's invariant. So I can write whatever's happening in the lab is equal to whatever's happening in the center of momentum. Okay? So if we do that, then what we're going to get is the following. So I'm just going to very quickly write these results down. So this guy is going to be PA mu plus PB mu, PA mu plus PB mu, where I'm not telling you if those mu's are up or down. You'll figure it out in the lab frame. This is going to be minus EA over C minus MBC times the momentum, the 3 momentum PA. That's the dual vector of this. Okay. Remember, the dual vector is just going to pick up a minus in this term, so that's why I got minuses here. And then, of course, this is just PA. And then the vector here will be EA over C plus MBC PA. Okay? And then we just multiply this out. And if we do that, we're going to end up with minus EA squared over C squared minus MB squared C squared minus 2EA MB plus PA squared. Okay? Yeah.
How did the first term of the final become E?
This?
No, like in the vector. Yeah. How did that be? I thought it was like MCC plus MCC. How did that become that?
It's,
oh, sorry. You're looking at, okay.
Yeah.
I thought we were doing something else.
No, that's fine. Okay, so there's our final expression. But I want you to notice something. Remember that formula I wrote on the board and put a block around? Go back and look at that. Tell me what that combination is. Yeah, this is the mass shell condition. So this is actually gonna end up being minus ma squared c squared. All right? That is, I can get rid of this unknown energy, unknown momentum in place of just the rest mass energy of this particle. The energy that I'm trying to solve for is still in here. That's good. Okay? So now I'm going to set that equal to this. Let me very quickly bang out that. This is just going to be PC mu plus PE mu plus PD mu plus PF mu, PA or C mu plus PE mu plus PD mu plus PF mu. Okay, we've already got this. It's this. The dual form of it's just going to carry a minus. Okay, so in the end, this is going to give me, and I'll just do it, I'll cheat. I'll say MC C plus MB C, whoops, C plus ME C plus MF C squared. All right? So at the end of the day, setting what is the invariant form of the initial momenta squared in the lab frame equal to the final momentum squared in the center mass frame, which I can do because it's invariant, I basically get that this has to be equal to this. Notice, this is an equation with one unknown, given that I know all of the masses. Okay? So you can find from this the expression for the energy A as a function of all the masses. I'm not going to do that. That's algebra at this point.
Oh, I noticed that in the vector, I think that should be MBC. I think you said MAC.
Here,
Yeah,
that's a B.
it is?
Yeah, it's a really dinky B, but it's a B.
Oh, okay, sorry, I couldn't see.
That's okay. Okay. I mean, no one wants me to do that algebra, do you? Please say no. The good thing is that you can take the result and extract it to an arbitrary number of particles. Because all it's going to do is it's going to grow this. Okay? So again, I just want to point out two of the most important tricks which often get used in these relativistic scattering calculations. One is, if you square things to make invariants, then you can set quantities in different reference frames to be equal as long as you're doing invariants. And secondly, this mass shell condition, which we don't have in non-relativistic physics, but in relativistic physics we do. This comes in handy quite often. Okay? Any other questions? All right, guess what you're going to have on your homework? The second part, because you wanted to see the first part. I'll see you on Tuesday. Get ready, because it's going to be a pretty